Hello, good evening, everybody. So thank you all for coming. This is the going to be an excellent talk on Curiosity, the next Mars rover. It's being given tonight by Matt Wallis, who's the lead system engineer on the program based at NASA's JPL in Pasadena, California.
Okay, well, I'm here to talk to you about the Mars Science Laboratory and the Curiosity rover. I'm going to try to keep moving along. I have a tendency to be a little long-winded on the subject, as you might imagine. So I'll try to get through it and leave some time at the end for questions and answers. So I thought I'd start, though, with an attempt to answer the question, why? Why go to Mars at all? And there are a number of reasons. I think, in the late 19th century, a number of amateur astronomers were peering through their fairly rudimentary optical telescopes and looking at Mars, thinking they saw canals. And that, of course, began the era of H.G. Wells' War of the Worlds, and Invasions from Mars, and Buck Rogers, and Ray Bradbury and the Martian Chronicles, and so on and so forth. But eventually, the telescopes got better, and our science instruments got better, and we flew some spacecraft past the planet, and we started to learn a little bit more about it. It got to the point where we recognized, of course, that there was no life, at least not life like us on Mars, and yet it still held the imagination, of the science community and much of the public. And I think one of the reasons is Mars is not that unlike the Earth. It's a rocky planet, unlike the giant gas planets of the outer solar system, and in that way it's similar to our own planet. It's the inclination or the tilt of its axis is actually almost exactly like that of the Earth. It's got a 24-hour day, or very close to 24-hour day. Much like our own planet. It has seasons, it has poles, and a diurnal cycle much like our own. So there's a lot of similarities, and we've come to appreciate the fact, even more so, that the surface environment on Mars was much like our own planet at one point in its history. And so for those reasons, it's continued to be a target for our scientific and exploration missions. In the mid-1990s, this rock over here on the lower left-hand side, Allen Hills 84001, it's an asteroid that was picked up in the Antarctic, and it was determined by the mid-1990s or so, mid to late 1990s, to have originated on Mars, and many tens or hundreds of millions of years ago came off the planet and eventually landed in the Antarctic. And inside this rock, there were certain signatures that you can see up here in the top left, associated potentially with organics and biosignatures. And so the debate began. Could there have been ancient microbial life on Mars at some point in its history? And that fueled the modern exploration cycle for Mars, which began on July 4th, 1997 with this mission. This is the first mission, Mars mission I worked on, and it carried a small 25-pound rover called Sojourner, seen here, cocooned inside this set of airbags. The mission was designed to demonstrate a low-cost and reliable mechanism for landing on the surface. You'd see a picture taken from the rover looking back at the lander and the ramp that it had driven over on top of the deflated airbags. It was a very successful mission, but it carried only about 5 kilograms of science equipment with it. And so it was very limited. It was designed the rover was only designed the last 7 days. It lasted about 3 months, but eventually succumbed to the Martian winter. And so in 2003, we launched another set of spacecraft. These might be a little more familiar to you. This is Spirit and Opportunity, seen here with its progenitor, the Sojourner rover. And as you can see, these two vehicles were much larger. And in this, with this kind of a platform, we were capable of carrying about 50 kilograms of science equipment. Sorry, about 50 pounds of science equipment to the surface of Mars. And the objective of this mission really was to follow the water, to determine whether or not there could have been, at some point, surface water on Mars. And when we landed, the first spacecraft landed in a place called Gusev Crater. The second one landed at a place called Meridiani. Both of these sites were chosen by looking at science data that came off our orbiters. And we were uncertain as to what we were going to find in each case. However, as soon as we landed the second mission, Opportunity, in a little crater called Eagle Crater, and we started taking imagery of this crater, we could see bedrock over here. And it turns out that these rocks, when we got a little closer with the rover and got some pictures, were pretty clearly sedimentary rocks, and they had certain accretions, hematite accretions in them that was indicative of an aqueous process. And so, essentially, this mission, Spirit and Opportunity, demonstrated that at one time Mars could have looked very much like this, with the type of surface water that we see here. In oceans and lakes and that type of thing. And we know that life on Earth requires three things, basically. It requires energy, which we get from the sun, as does Mars. It requires water, which Spirit and Opportunity now had pretty unequivocally demonstrated existed on the surface of Mars at one point. And the third thing that's required is carbon. And that's where this mission comes in, and our Curiosity. This is the rover that is on its way to Mars, and will be landing in about 3 weeks. As you can see, it's quite a bit larger than than Spirit, Opportunity, and Sojourner. Weighs in at about 1 ton, and it can fairly easily, with its arm up in the air, touch the basketball rim. At 10 feet in the air. It carries, unlike, as I mentioned before, Spirit and Opportunity carried about 50 pounds. This carries almost 500 pounds of scientific instruments and sampling systems and observational systems. And so it is far more capable than anything we've ever landed on Mars. Now, getting something this size onto the surface of Mars is not an easy thing to do, as you might imagine. Actually, getting almost anything to the surface of Mars is not necessarily an easy thing to do. And so it requires us to put it inside a spacecraft and to launch that spacecraft and successfully land that spacecraft. And what I'd like to do is orient you a little bit with the spacecraft and the engineering systems of the spacecraft. And then I'm going to show you a quick animation and give you a sense of how this whole thing is supposed to go on August 6th. So here's the rover. As you can see in its stowed position, we break the mobility system. It lays pretty flat. It allows it to fit reasonably well inside the entry capsule here. This is the top of the entry capsule, what we call the back shell, and this is the heat shield, which absorbs the entry heating environment. Attached to the rover, or the rover is attached to, something we call the descent stage. The descent stage is a part of the system that flies out the last kilometer or so of descent down onto the surface of Mars. And it has the propulsion systems and navigation and control systems necessary to put the rover down on the surface. Up on the top is the cruise stage. This is something that's that we discard as we're getting ready to enter the outer atmosphere, but it has a number of the systems that help us get from Earth to Mars. And so what I'm going to do is show you a quick animation, give you a sense of how this system should work and is working, and then I'll talk in a little more detail about the system itself. So here you see the spacecraft on top of the second stage of the Atlas vehicle. It essentially gets us pointed in the right direction. It gives us enough C3 to exit the gravity well of the Earth. And it spins us up to about 2 revolutions per minute. And then the spacecraft sitting on the top here separates, and it's on its way to Mars at this point. We spin to maintain the stability of the system during cruise. It's about an 8-month cruise to get to Mars. We're almost there. As I said, we're only about 3 weeks away from landing at this point. During the cruise phase, we go through a number of trajectory correction maneuvers. By the time we get to Mars, after having traveled 350 million miles, we've actually hit a spot on the outer atmosphere of Mars. It's about 1 kilometer, perimeter of about 1 kilometer. And as you can see, we've discharged the cruise stage, and we're now, this is the entry capsule entering the outer atmosphere. We're firing the thrusters to orient ourselves during the hypersonic guidance period. At this point, we're traveling about 17,000 miles an hour relative to Mars. The heat shield's absorbing most of that kinetic energy. It can get to about 3,800 degrees Fahrenheit during this period. Again, we continue to fire these thrusters. We have a lifting body. It's a mass offset body. And by rolling the body left and right, we can actually guide ourselves through that phase of the entry. We fire off some ballast mass to straighten ourselves up, and at a speed of about Mach 2, we deploy the parachute. After the parachute is deployed, the heat shield comes off, we turn on our radar, we start trying to get a ground surface solution. And as we get about 1 kilometer from the ground, we release the powered descent vehicle. Powered descent vehicle has both the rover and the descent stage on it. At this point, we're still traveling at about 1,000 miles an hour. We drop about 200 miles an hour, and we drop down to about 2 miles an hour before we touch down on the surface of Mars. So the descent stage is taking out the rest of that velocity. And in a moment, what you're going to see is a move we call the sky crane. Sky crane is a unique part of this landing system, where the rover will actually separate from the descent stage. It's modeled after the heavy lift helicopters that you've probably seen before carrying the large payloads. And it gives us a couple of unique capabilities that we didn't have inside the airbags. In particular, the ability to land this much mass. So as we touch down, the compliance in this bridle here, it's about a 21-foot bridle, gives us a few critical moments to understand that we have touched down before we cut the bridle. The descent stage then flies off and crashes, essentially, and the rover is ready to go on the surface for the most part. We need to do some deployments, raise the mast, but unlike previous missions, one of the advantages of this particular landing system is that we're on our wheels. There's no pedals that need to unfold. There's no airbags that need to be deflated. There's no lander system that we need to drive off of. And so that reduces the inherent risk after landing of getting the mission going. So that's essentially how the system is designed to operate. And what I'd like to do is spend a few minutes showing you some of the hardware. This is the full spacecraft in the thermal vacuum chamber. It's the diameter of the entry capsule is about 4.5 meters. We'll talk some more about that in a minute. This is the top of the cruise stage. That's the element that you saw separate just prior to Mars entry. So you can see we have solar arrays that provide the power for most of the trip to Mars. This is a launch vehicle adapter. And then if I flip this upside down, what you see on the bottom of the cruise stage is some tanks, as well as electronics, thrusters, that type of thing, as well as some star scanners and sun sensors. This is the top of the entry vehicle, or what we call the aeroshell. This is the back shell during assembly. As you can see, there are a number of different holes here and doors for mostly for assembly purposes. These up here are where the thrusters for hypersonic guidance protrude through the top of the back shell. Some people don't have a very good sense of scale for this system, and so we took this Somebody once asked us, what can you fit inside this entry capsule? And somebody calculated that we could fit a Mini Cooper. And so after assembly of the back shell, we actually took it outside and put it over a Mini Cooper just to prove that we could get a car inside this thing. This is the heat shield. It is, as I said, about a 15-foot heat shield. It is the entry capsule itself is the largest entry capsule ever flown. It's quite a bit larger, actually, than Apollo. It's larger than Viking. It's almost double the size of our previous Mars missions. And so it was a real challenge to assemble and to test this particular part of the vehicle, but it was what required to get the full mission down. This is the heat shield with its protective tile. Much like the shuttle has a tile to protect it from heating during entry, our heat shield uses a phenolic impregnated carbon ablator, and that's what these tiles are for. This is our parachute. It's the largest parachute we've ever built. It's about 70 feet or so across in diameter. It's being tested in this particular picture in the largest wind tunnel in the world at Ames Research Center in California. Just to give you a sense of scale, this is a human being over here. This is the descent stage, which I mentioned before provides the propulsive capability during the last part of the entry, descent, and landing system. This is really a spacecraft almost unto itself, and what I have here is a quick 360 tour, which will take you around the descent stage. Actually, the rover, in this particular picture, you can see the rover mounted up underneath it. You can see our main engines. There are 8 of these 4,000 Newton engines. They're derived from Viking, actually, which was one of our first Mars lander. And up here you can see some inertial reference units, IMUs, as well as some additional control electronics. There's propulsion tanks and pressurant tanks. And you can see the thrusters up here that poke up through the top of the back shell that provide the hypersonic guidance control capability. Over here, it's blanketed up. It's our pulse Doppler radar. I'll show you another picture of it, which is critical for the Sky Crane landing system to successfully land on the wheels. And again, coming back around to our avionics bay, which is where most of our computational motor drive and power distribution systems exist. So, quick tour of the descent stage. This is something we had never attempted to build before, and it's really, it was quite a challenge to build the structure and to integrate all of this equipment onto the vehicle. This is looking up at the descent stage up here with the rover on the bridle in the foreground. You can see the robot arm on the front of the rover here to keep you oriented. Obviously the wheels. These are the 6 beams of the pulse Doppler radar that I mentioned before. This was a brand new development for us. As you can imagine, the success of the mission really depends on us getting our velocities down to a point where it's safe to land on the wheels. And so this radar had to be extremely capable. You know, it's the accuracy of the system, even at 11 kilometers above the surface, is remarkable. You know, it's on the order of meters for altitude, and it's a handful of meters per second in velocity. And so, very capable system. This is the top of the rover. You can see our mast. This is our imaging mast actually stowed for launch along the top. These are small inlets in the chassis. Some of the more critical science instruments sit inside the chassis below these inlets. And the rover system is designed to actually to sample rocks and to put that sample into these analytical instruments inside the vehicle. And so we have a percussive rotary coring system on the end of the robot arm. First time we've ever attempted to do that. And so another particular challenge on the rover. You can see this differential that runs across the top of the vehicle, which connects the port and starboard mobility systems. This is the end of the robot arm. It has, as I mentioned before, this rotary percussive drill. The idea is to get inside the outer layers of the Martian rocks. Since the outer surfaces were exposed to the radiation environment of Mars, the science community wanted to get behind those outer layers and drill actually into the rocks. It became a real engineering challenge to figure out how to do that from 100 million miles away reliably. But we ended up with this drill that sits here. We also have a sieving and portioning system here that provides the small amount of sample to the instruments, as well as 3 different contact instruments out here on the end of the robot arm. The whole turret weighs about 30 kilograms, or about 70 pounds or so. Just the turret alone actually weighs more than all the science instruments on Spirit and Opportunity. If you flip the rover over and you take the belly pan off, this is what you would see. This is all the electronics that need to be maintained in a thermally controlled environment. And so we have our computers, our power distribution systems, our telecommunication systems, our motor drive electronics, and all the body-mounted instruments as well. One of the critical instruments is this one here. This is the large analytical instrument that we call SAM. This is the one that's in particular designed to look for those organics, those carbon compounds, which I mentioned before, that third leg of the life triangle. And this instrument alone would not have fit into either the Spirit or Opportunity chassis. And so it gives you a sense of the size of this vehicle. Curiosity carries 10 different instruments. I mentioned SAM down here, which is the analytical laboratory. It has a number of other instruments which are body-mounted for chemical analysis, as well as to monitor the radiation environment. We have a Russian neutron emission instrument, which is designed to look for subsurface ice, actually. We have a descent imager. We'll get pictures as we're coming down from the rover of the surface for context, as well as just because it's going to be a cool-looking picture to share with everybody. We have a couple instruments out here on the arm, and then there are 3 mounted up on the mast as well. One of the instruments that we have, I'll mention, is this laser, and we call it the death ray, but it's designed to essentially create a plasma. It fires the laser. It creates a small plasma cloud at the target. That plasma cloud is then imaged by a spectrometer, and we can essentially gives us standoff remote capability of understanding what the chemical nature of some of the rocks are. That allows us to quickly assess the rocks that we're interested in, and not waste time driving up to, approaching, putting the arm on rocks that, for instance, may not be of particular interest to the science community. So it's a nice remote sensing capability. As you might imagine, we spend a lot of time testing this system, and in particular, as I said before, when we moved away from the airbag systems and into the sky crane system, we had to come up with a lot of unique verification paths for this. We can't fly to Mars without spending an awful lot of money, and it's a hard thing to do on the Earth, but we do the best we can to replicate the environment and to test the system to make sure it will safely touch down. And so what I thought I'd do is show you just a couple clips from some of this touchdown testing that we did. This is a vehicle we call the Scarecrow. As you can tell, it's not fully loaded, but it's about the right mass for Mars, roughly speaking. And so it's hooked to a crane, a real crane, in this particular case. And what we do is we're dropping it. This is a real-time video. It gives you a sense of about how fast the vehicle is going to come down on Mars. Without the bang, hopefully. So that didn't look too bad on a flat surface. So we said, hey, maybe we better do a few more aggressive cases. And so we built up the vehicle. We built up another vehicle that has higher fidelity. We created some, put it on a 20-degree incline, put some rocks, dug a trench, and took a look at how the vehicle would respond to these types of boundary case environments as well. And the vehicle does very well. The system itself, as you can imagine, is designed to traverse across a fairly aggressive surface environment on Mars. And the concept behind Skycrane was to use that to our advantage, not replicate that with landing legs and other things. Essentially use the mobility system and the compliance in the mobility system to safely touch down. And the concept has tested out very well. It's very mass efficient. And the rover does very well in these types of landing conditions. It's actually more capable, the slope and the rock density and the rock heights that this system can tolerate is substantially better than our previous missions. And so it allows us to get to certain places on Mars that we couldn't get before. And I'll show you some pictures of what I mean in a bit. This is another Skycrane test. In this particular case, the idea was to test the deployment of the mobility system. After the rover separates from the descent stage, the mobility system has to deploy. And as that mobility system deploys, it creates loads, as you might imagine, back into the structure that ripple back up actually into the bridle, and into the controller of the Skycrane system itself. And so we went through a fairly extensive integrated test, what we call the full motion test, to simulate the rover deployment and the mobility deploy. As you can see, there's no wheels on this mobility system. And again, that's to replicate the roughly 38% of the Earth gravity that we have on Mars to get the loading and the mass right for this particular. This is what it would look like if you were Martian, standing, looking at this thing coming down at you. So pretty exciting. Now I know what you're thinking. Sounds like you guys do a lot of cool things, and we do a lot of cool things. But do we get to blow things up? That's, I'm sure, one of the questions you have for me. And so here's the answer. Yes, we get to blow things up. This is a parachute deployment test. Actually, we're launching the parachute out of using the largest mortar ever fired. This is a slow speed, high resolution image of the parachute coming out of its canister. And here's the shot of the full parachute being deployed in that wind tunnel that I mentioned before. You can see it takes a little while for it to open. On Mars, traveling at Mach 2, however, this will open in less than a second. There we go. There's the canopy opening up. It's agonizing when you watch this in real time, hoping that the parachute's going to open in the wind tunnel. And that you're not going to have a failure. But on Mars, as I said, it's going to open almost instantaneously because of the speeds we're traveling at. And absorbs an impact or an impulse of almost 60,000 pounds as part of the inflation loads. Largest parachute we've ever built. It's a disc gap band parachute. You can see the gap here between this band and the disc on top. That's for control, for additional stability of the system. This is a picture of the rover going through a mass properties test. For all of our systems, we have to understand exactly where the center of gravity is and what the properties of inertia are. And so we put all of them on spin tables or on turnover fixtures. This happens to be the rover on a vertical position getting tested. This is the rover over here on the right-hand side of this picture. We're doing some imaging testing here. You can see all the targets and the lights set up. We have 17 different cameras on the vehicle. Science cameras, navigation cameras, hazard avoidance cameras, descent cameras. We have a microscope out on the end of the robot arm. And so it takes a lot of work to get all of those cameras both geometrically and radiometrically calibrated. And so we spend a lot of time pre-launch doing that type of This is a shot of the first drive test that we ran on the vehicle. Now, when I talk to the kids, they're always disappointed that the rover doesn't drive faster. But I tell them it's like the tortoise and the hare, you know. Eventually it gets there. It does just fine. But it only moves at about 6 centimeters a second. That's about the same speed as our previous vehicles have traveled. It's less than 1/10 of a mile per hour, to give you some sense of how fast that is. But that's okay, because obviously we're doing a couple things. One is we're not traveling that far every day on Mars. We just want to get generally from one place beyond our local region so we can see what's around us. And so it's capable of traveling over 100 meters a day despite the relatively slow speed. We also need to be very aware of our power usage. This vehicle is not powered by solar arrays. It's powered by a thermoelectric generator. And so the amount of power that we have available to us is about 100 watts. That's how much the radioisotope thermoelectric generator generates, about the power of a light bulb in your house. And so we have to be pretty fastidious about how we use that energy, and that's one of the reasons we drive relatively slowly as well. It's a 6-wheel vehicle, just like our previous systems. It has a rocker bogie suspension system, capable of driving over hazards that are a couple feet high. It's a very stable platform, and it's actually a very capable climber. So it's a strong system. This is some footage of arm testing. Now, in this particular case, the arm moves so slowly that we've speeded it up here, as you can see, by a factor of about 6. And in this case, we're using a substitute turret out here on the end of the arm. It doesn't have all the mass. Again, for mass reasons, it doesn't have all the mass that the flight turret would have. Here we're doing some tilt testing on the flight vehicle. It's designed to operate on slopes up to 30 degrees, although we try to avoid slopes that are that high because we do have a tendency to slip. And so it's been well tested. This is this is a picture of some testing that we did for the radar system. As I mentioned before, the radar is a brand new system, and it's critical to ensure that we land at a speed that the system is capable of absorbing when we touch down. And so to simulate the last few meters of the sky crane delivery system, we hang a sort of simulated, a partial rover out here below a helicopter. This is actually a movie helicopter with a gimbal on the front where they would normally mount a movie camera for those action, footage shots. In Los Angeles, we have a lot of these things, it turns out. So what we mounted was our radar on the front, and we took it out into the desert, and we did simulated sky crane testing for see how the radar performed, to see what the radar return signature looked like from the vehicle, for instance, when it's hanging down below the descent stage, and that sort of thing. For the upper portions of the entry descent activities, as I said before, at parachute deploy, after parachute deploy, we're still moving at about 1,000-ish miles an hour, and we're still pretty high off the ground. We can't simulate those kind of vertical velocities in a helicopter, and so we put the radar inside a pod sitting out here under the wing of this F-18, and we took it up and allowed the F-18 to simulate the entry, descent, and landing landing profile that we needed to test the radar. This is a picture of the rover in a thermal vacuum chamber. As you might imagine, we do everything we can to simulate the Mars surface environment and to test the vehicle in an appropriate environment. So we put it inside our 25-foot thermal vacuum chamber. We have a solar simulator. That's what this guy is doing. He's calibrating the solar the solar simulation, which is a column-nated light source that comes down onto the vehicle. And then we close, after we get this guy out, we close up the chamber, we pump it down, and we flood the shrouds with liquid nitrogen, and we cool it down. One of the challenges we have on all of our surface systems is to deal with the thermal environment on Mars. The days, actually, the summer days, can get reasonably balmy, to about 20 degrees Celsius or so in the middle of the day if you're sitting at the right spot. And maybe wearing black, I don't know. But at night, even during the summer, the temperature drops dramatically down. During the winter months, at some of the latitudes we were designed to operate at, the temperature gets down essentially to the freezing point of the carbon dioxide atmosphere. And so it's minus 130 degrees Celsius. And every day, pretty much, you go through this thermal cycle. And as you all can well imagine, that is a very stressing environment for a lot of our materials, clearly for our electronics, and so we do a lot of testing to verify, in fact, and a lot of design work to show that our systems are capable of those types of thermal cycles over a long duration, long period of time. And so that's part of the testing that we did in the chamber. This is a sky crane test, as we call it. In this particular test, we were assessing the robustness of the vehicle to EMI, or electromagnetic interference. After the rover is deployed, and actually before the rover is deployed, we've got telecommunication systems, both X-band systems and UHF systems transmitting. I mentioned before we have a Ka-band radar, and of course we generate a lot of electronics noise inside the control systems and power systems as well. And so one of the things we're very careful about is to verify, in fact, that we're compatible with ourselves from an electromagnetic perspective. This is a particularly difficult, particularly challenging task, in part because of this bridle. This bridle is not only mechanical, but it's electrical as well. The brains of the system sit down here in the rover, and so all the control signals up to the descent stage are sent through an electrical bridle that connects the two. And many of our sensors, our radar, for instance, and our IMU up here, provide critical data that has to come down to the rover during entry, descent, and landing. And so any corruption of that data, of course, could be fatal. And so we spend a lot of time doing this type of testing in multiple different configurations to verify, in fact, that we have a system that will perform as we expect. I always show this picture because I just like it. Eventually, we did finish testing the system, and we put it in a military cargo plane, and we flew it down to Kennedy Space Center. It was about 13, 14 months ago, I guess, is when we shipped the rover in the descent stage down to the system. We reassembled the entire spacecraft actually down there, and we integrated it on top of the Atlas, and we launched it in late November of last year. The cruise so far has gone very well. I mentioned we've gone through a number of instrument checkouts, engineering, hardware checkouts, entry, descent, and landing system checkouts. We've executed a number of trajectory correction maneuvers to get us into the right spot so that we can hit our target on Mars. And so we've uploaded the final software just over the last some number of weeks for entry, descent, and landing. And so we're at a point now where we think we're pretty much ready to go. The whole entry, descent, and landing activity from the time you hit the outer atmosphere to the time you're on the ground is about 7 minutes long. Light time for Mars is about 13 minutes. So there's no controlling this system. It's on its own. It's completely autonomous. And this is certainly the most challenging part of the mission coming up in 3 weeks. And we're all looking forward to it. Where are we going? This is where some of the previous NASA missions have landed. Curiosity is going over here to a reasonably equatorial site called Gale Crater. This is a picture of it. You can see the outer rim actually of the crater. And in the middle, there's this kind of mountain. One of the things the scientists like to do is to find the stratigraphic records, if you will, on Mars. In other words, they want to see the vertical history of the planet by looking at exposed cliffs or exposed crater walls and those sorts of things. And so when we started looking for a landing site, the craters were of particular interest to the science community. But the mountains were also of interest to the science community. So we want a crater, we want a mountain. We found a place, we had both, actually. This is, as I said, it's a crater with a mountain in the middle of it. And what essentially happened a couple billion years ago is an impact crater that eventually, over the course of time, filled in probably with sedimentary material, and then portions of that material were then eroded away, leaving this mound in the center. And so we are landing here in this relatively small landing ellipse, and then the idea is, after a period of time of checking out the engineering systems, that we would begin a tour up the slopes of Mount Sharp to start looking for the type of science targets that the community is particularly interested in. Now, this is the first, I think I mentioned briefly that as we're in the hypersonic phase of entry, we have the ability to actually steer the spacecraft. It's mass offset, so it's essentially a lifting body as we're coming in. And then the thrusters roll that lifting body to the left, or counterclockwise, or clockwise, if you will, to bank the system and essentially steer it in to a targeted landing site. And by doing that, we were able to reduce the size of the landing ellipse from our previous missions. This is a landing ellipse from the Viking mission. This is the Pathfinder Sojourner mission here. You can see Spirit and Opportunity. This was the landing ellipse, the uncertainty band, if you will, for landing those two missions. But to get to someplace like Gale, where you have this rim, which is clearly a hazardous object to be avoided, as well as the mountain, another hazardous object to be avoided, we had to really improve the landing capability of the system, and that's why we do the guided entry and the propulsive descent on the sky crane. Our landing ellipse is about, well, you can see it, 19 kilometers by about 7 kilometers. Downrange is always a little harder to control than the cross range. But we have good confidence that we're going to land inside the ellipse, and it wouldn't surprise me to get pretty darn close to the center. Once we land, as I mentioned before, there's an area in the basin down here that looks like an alluvial fan to many of the science community, and so we'll likely spend some time looking at that area down here, and then start making our way up the side of the mountain. In particular, there's a number of clays. Clay obviously forms in the presence of water, and water, as I said before, is one of the keys to life. And so the science community want to look at these phyllosilicates and clays that are located down towards the base of Mount Sharp, and we'll probably spend quite a bit of time down there. Eventually, we'll work our way up to areas where they see salts and some sulfate compounds as well. And so that's where we're headed. So I went through that very quickly in an effort to leave some time for questions and answers. But just to finish off here, I thought it'd be nice to show you a picture of the sort of 3 generations of Mars rover with this handsome fellow standing right there behind him. It's been a very challenging development cycle for this particular mission. Putting a ton down on the surface of Mars is not an easy thing to do. But we're about to hit the payoff period, obviously, with the landing coming up in 3 weeks, and we're all pretty excited. I hope you all can tune in early in the morning of August 6th. We'll be landing at Gale Crater. So thank you very much. Thank you.
Well, thank you very much, Matt. A very interesting talk, and I don't think anyone can doubt your ambition when you've seen what an ambitious program you've got there. I just wish you a lot of success. I'm sure we've got lots of questions. We've got one roving mic here.
Hi, David Hindley, National Physical Laboratory. I was fascinated by the precision with which you hope to hit your landing ellipse. What kind of navigation are you using to get to that kind of level of precision?
Yeah, good question. The question, I think everybody heard it. The question was essentially what kind of navigation do we use to get the precision that we get for the landing site? We travel about 350 million miles during the course of the cruise cycle. And as I said, we hit what's called an entry plane or a B plane that's about 1 to 2 kilometers across. And so somebody told me it's like hitting a golf ball in Los Angeles and getting a hole-in-one at St. Andrews. So I have no hope of either hitting a golf ball in Los Angeles or getting a hole-in-one. So it sounds pretty tough to me. But the way we do that is with radio navigation, Doppler system, Doppler measurement systems from our X-band radio system. We use something called delta doors, which over the course of decades, JPL has actually gotten very good at using. All those signals are received at the Deep Space Network stations that we have centered around the globe, and all those Deep Space Network systems have special digital processing or signal processing systems that give us the data that we need essentially to understand where the spacecraft is. And so that gets us to about 1 to 2 kilometers, as I said, of accuracy when we hit Mars. Unfortunately, at that point, a whole bunch of other errors start to get introduced when you hit the outer atmosphere. We no longer have a radio signal that we can close the loop on and control the attitude or the position of the spacecraft. And so we use our initial measurement capability, our IMUs, to essentially dead reckon our way down towards the ground. We are subject, unfortunately, to a number of errors associated with the alignment of those systems, as well as just the aerodynamic variability in the atmosphere. I would say one of the most challenging parts of these systems is not the engineering, the elements that you understand and can specify, but it's trying to understand what Mars is going to throw at you, and this is a perfect example of that. There's a lot of variability in the atmosphere. We take a quote-unquote weather report every day, actually, and we'll do final updates of our navigation parameters based on how the atmosphere is looking relative to density and winds and things like that. And so we have to account for that as best we can, but we introduce something on the order of 7 kilometers of error as a result of those uncertainties after entry into the atmosphere. And then once we actually deploy the parachute, we're subject to the winds, and the winds can take us again another 3-ish, 4-ish kilometers from our target. And so that introduces another error, and even once we come off come down into the powered descent, the propulsive descent phase, where theoretically we could fly out some of our uncertainty, we don't do it mostly because we don't want to expend the fuel. We want to maintain our fuel margin for landing. So some of our future missions, actually, we're looking at something called terrain relative navigation, where as the heat shield comes off and we have a view to the ground, we'll image the surface of Mars, we'll look at features, we'll have onboard maps essentially to tell us where we are, and after we drop then off the parachute into the propulsive descent phase, we can actually spend some fuel and fly ourselves even more to an even more precise location on Mars. But that's how we get there, and those are some of the errors that are introduced in trying to hit the target.
Just one other related question to that. Once you get to within a few meters of the surface, is there any system that actually says, hey, I can detect a very large rock I really don't want to land on, let's move a few meters to one side? Is there such a system?
Yeah, that's a good question. It's what we call hazard avoidance. And we went through a system trade to determine whether or not we should add that level of complexity to this vehicle. It obviously, not only does it potentially introduce some robustness, but it can introduce error sources. You can get spoofed by it as well. And so what we decided instead was to use our orbital imaging capability. We have 1 meter, half meter resolution imagery of all of our potential landing sites, and essentially do a rock size characterization to determine probabilistically whether or not we could potentially land on a rock that could dead center us, for instance, on the bottom of the vehicle, or whether or not we could potentially land on a slope that was too great. And we sub-select our landing sites based on those engineering constraints, rather than put the onboard smarts to avoid a hazard. And that was the trade we went through many years ago, and that's what we do. We are looking again some future systems. We're looking at doing that, using downward-looking lidars and different types of hazard detection systems that we could then avoid, certain hazards for the touchdown. It's a good question.
The previous generation of rovers well exceeded their expected lifespan. What do you expect to be your sort of lifespan for this current rover?
Yeah, so the Opportunity is still going. Opportunity was designed for a 3-month mission life, and here we are 8 years later. It's a little embarrassing, actually, because I won't go into the details, but these are systems that are designed to be high reliability by their very nature. They have to be, even to survive, a week on the surface. It's a very harsh environment, and you have to have a high reliability system to get yourself to the surface and to get through the space environment and all those sorts of things. And so once we land, once we get through, especially the seasonal variation on Mars, there's not a lot that can take you out necessarily. The Voyager spacecraft are a good example. They're still going. Here we are 40 years later. Obviously not designed for that type of mission life, but as harsh an environment as the space environment is, and the Martian environment is, it's pretty deterministic, And so the systems tend to last longer than they're designed for. This one's designed to last for 2 years, 2 Earth years, which is 1 Mars year. And so it had to have the capability of dealing with dust accumulation on the rover, for instance, which was a problem that plagued Spirit and Opportunity because they're solar array powered. Spirit, in fact, died as a result of not having enough electrical power to keep itself warm. And Opportunity went through a number of challenging winters that they managed to get through. That's one of the reasons why we put a radioisotope power source on this particular vehicle. So this system is designed, architected really to be robust to a lot of the environmental factors on Mars, and it has more redundancy. The other surface missions were all pretty much single string. This has not everything's redundant, but it has a number of components in its system that are redundant. And as I said, it's much better at dealing with thermal variation, the dust accumulation, all those sorts of things. So it could go longer than 2 years. Wouldn't surprise us to see an extended mission beyond that. I think the thing we most worry about is the mechanisms. There's 33 different mechanisms on the rover, and they are all have wear failure modes, as you would expect, in the gearboxes and so on. And so that's the part of the mission that could potentially limit the life.
Before we take another one from the audience, I'm particularly interested in the landing phase. When it's landing on the descent module,
right.
The descent module's firing these 4,000 Newton thrusters.
Right.
Are you concerned about the amount of sort of dust make it flick back up and create a big cloud that it's trying to land through?
Yeah, we are actually. We did a lot of CFD analysis to look at what the plume and the plume impingement on the surface was going to do relative to the dust environment. And based on that, I'm not sure if I don't have a picture up, but we angled the engines out by about 25 degrees, and we positioned them in such a way that the rover, they're actually not equally spaced around the perimeter of the descent stage. They're off to the sides of the vehicle. And as a result of how we position the engines, as a result of we actually sized the bridle, taking into consideration that particular analysis and the impingement and the dust clouds and things like that. And so sitting 20 feet or so above the surface, angled out at 25 degrees, we will still excavate some part of the surface, but we have convinced ourselves that particular plume, not only the dust plume, but also the engine plume, we don't want to contaminate our science instruments with hydrazine, that we're okay. When we cut the bridle, actually, we do a specific maneuver to avoid putting the engine plume down on top of the vehicle or to getting it too close to the vehicle as well. And so it took some specific modeling and wind tunnel testing. It took a lot of CFD analysis and that sort of thing, but we feel pretty good about it. The Phoenix lander and the Viking landers, obviously the engines were much closer to the surface, and they did see that kind of a problem. But we think that's one of the advantages of Sky Crane. It keeps the engines far enough away from the surface.
Two questions, if I may. Firstly, the heat shield. What has that got to cope with in terms of density? Is it relative to the Earth's density? And secondly, Mars experiences violent dust storms from time to time. Yeah. How have you designed and tested for that situation, both on the heat shield and the descent Sky Crane system?
Yeah, so density, atmospheric density. The Martian atmosphere is only about 7 torr, 1% or so of the density of the Earth atmosphere, which is one of the reasons it's very hard to land on Mars, by the way, because, on Earth you can simply deploy some parachutes and after your initial deceleration inside the aeroshell and land safely. But on Mars you can't do that. There's not enough atmosphere to slow you down enough to safely land. So we have to use these propulsive systems. The heat shield is capable of absorbing the kinetic energy associated with that. It essentially drives us from about 17,000 miles an hour to about 1,000 miles an hour. And as I said, it is a specially designed tile, ablative tile that we take into arc jet facilities and we simulate the Martian environment and demonstrate the capability of that material to absorb it. So it's a challenging entry system, more challenging actually than some of our previous ones, in that the ballistic coefficient is so heavy. Despite the fact that it's bigger, it's such a heavy system compared to our other systems. The ballistic coefficients are very high, and so we entered into some heating regimes that we've never had to deal with actually before. At least we weren't aware of before in the testing that we had done on previous missions. And it forced us to actually go through a design cycle on the heat shield and on that ablative material. It was pretty challenging. So, but the system's capable of dealing with that. So the second question was, I'm sorry.
Violent dust storms on Mars from time to time. Yeah.
There are dust storms. There's regional dust storms and there's global dust storms, and they can cause a number of problems for us. The previous missions, as I said before, were a lot more sensitive to them, both from the thermal design of the system, as well as the power systems, because they're all solar array controlled. And when the dust gets heavy, you get less transmission, insulation from the sun, and so your power goes down. So that's a problem for the surface missions that are driven by solar arrays. As I said, this has essentially a nuclear battery. It's got a radioisotope source and that heat is then converted into electrical energy using thermoelectrics. And so we're a lot more robust to dust storms on the surface. The other problem that we have is in the landing system, because a dust storm changes the atmospheric conditions dramatically when it happens. And in fact, if one of these global dust storms were to hit on August 5th, there's a good probability that it would be very difficult for this system to survive the entry. However, they only occur at certain points in time in the Martian year. At least that's our observational history for the dust storms. And so we have targeted the landing and selected landing sites and targeted the launch dates to stay ahead of that time of the year. And so we don't expect to see a global dust storm at landing, but they can be problematic.
Hello. This all looks really fascinating and brilliant. A quick question about the descent stage. After it's finished and it sort of zooms off and crashes,
Right.
The
official word is impact. It doesn't crash.
Well, I just wondered, did you look at any other solutions, and how much mess is that going to make?
We did look at other solutions. We looked at the possibility of soft landing the descent stage somewhere, partly as an engineering test, partly just to avoid whatever comes of the impact. But the problem, as I mentioned before, is that the controller system is on the rover. So once you separate the rover, it's kind of flying blind. We basically send a final command to the engines on the descent stage to throttle up to 100%, and there's a very small processor that just maintains the stability of the system, and it's designed to throw itself as far away as it can throw itself before it runs out of fuel. We have a minimum kind of throw distance, and I forget, it's on the order of 150 to 200 meters, as I recall. So we maintain enough fuel to make sure that we're not going to land in an area that could be a problem for the vehicle, either scientifically or in any other way. Interesting though, just the other day I was, when we're landing, everybody's waiting for someone to, one of the engineers who's watching the telemetry coming back or the signals coming back or whatever, to say, hey, success, and then everybody cheers. And I said, what trigger are we using? Because I realized after all this period of time, I know what trigger on the spacecraft, obviously, that the spacecraft's using to control itself to say, okay, I'm done, cut the bridle, so on and so forth. But I said, what are we using on the ground to say we've successfully landed? What, is it a IMU measurement? Is it what is it? And the team that was responsible for doing all this operational work said, well, basically, we're going to wait for the touchdown command to get sent, and then we're going to wait about 10 seconds after that to see if we keep getting telemetry from the rover to make sure the descent stage hasn't fallen on it and killed our rover. So I said, okay, it's a long 10 seconds. It's gonna, but we think we can throw it safely away from the spacecraft. And we've had to actually control this contamination process that we go through called planetary protection, which you may or may not have heard of. But the idea is that there's an international tribunal, if you will, of scientists that tell you how many bugs you can take to Mars. And I don't know why, but it's 500,000 bugs is the number of bugs you're allowed to take to Mars. All dead. They all have to be dead. But the idea is to not forward contaminate the planet where you're trying to make these sort of life type of detections, obviously. And so we've had to do that type of, that level of cleaning and sterilization on the descent stage, because when it impacts, it could break up and expose the surface to these types of contamination, this contamination environment. Beyond that, there's no other problem with the descent stage flying away and impacting.
My name is Indranil. I'm from Logica. Thank you very much for a very fascinating presentation.
Sure.
What I wanted to ask you was, I saw a news item on BBC today that said that your orbiter is not in position to relay the information back to Earth for the last 2 minutes of descent. I was going to ask you, what plans do you have to sort of reorient your orbiter?
Right. So the question was associated with, I didn't see the news release, but apparently agency just made a news release that the orbiter, one of the orbiters that's actually monitoring the telemetry of the spacecraft as it's landing, was being essentially positioned in its final orbital position to be at exactly the right spot when we land. The orbiter passes over, the visibility to the orbiter is on the order of about 15 minutes out of its roughly 2-hour orbital cycle. And so to make sure it's in the right spot when we land so that it's collecting the UHF telemetry off the spacecraft, we had to make a final positioning adjustment on the orbiter a week and a half or 2 weeks ago, I guess. And unfortunately, we had just lost one of the reaction wheels on the orbiter, and so we had to spin up our skew reaction wheel, which is essentially the spare reaction wheel. It operates a little differently than the other reaction wheels on the orbiter, and so that final maneuver resulted in somewhat unexpected behavior of the spacecraft. And we've been looking at, and as a result, we did not put that orbiter exactly where we want it to be. Now, it has no effect on the success or failure of the landing. It's just there to record the telemetry coming back from the spacecraft. But that's critical telemetry. We want to see this, the system to the degree that we can while it's landing. And so when I talked to the program management a couple of days ago, they were still thinking about whether or not to execute another correction maneuver and try to get it exactly where we want it to be. I'm not exactly sure because, as I said, I haven't talked to the team in the last couple of days what the decision was. I think we still have a little bit of time to decide whether or not we can execute that maneuver or not. Now that we have another orbiter, actually there's two other orbiters around Mars right now. One is that's the Odyssey spacecraft, and it's a good orbiter because it was essentially bent piping, real timing the telemetry back to the Earth, and gives us that sort of real time indication of what's going on. There's another orbiter called Mars Reconnaissance Orbiter, which is also going to be recording the data, but it will be on the order of 4+ hours before we get any of that data back from the orbiter. And so we'll have the telemetry, the engineering telemetry. It'll just be a delay in what we see. And then there's a European orbiter, Mars Express, which will be recording in something called canister mode. I believe it's really only recording the carrier, looking at Doppler signatures and things like that. But that will also give us an indication of how things are going. But I think there's also a time delay on the Mars Express data as well. So that's unfortunately all I know about that particular orbiter. As I said, it doesn't really affect the success or failure of the mission. It just gives everybody an opportunity to follow along in real time. If we don't have that, I believe Odyssey will still pass over the site a couple minutes after we land. We'll collect all that telemetry, so fairly shortly after landing we'll have data.
Obviously, NASA's had great success with robotic missions, and we'll obviously everybody in the room is hoping that Curiosity is equal success. But where do you see the next mission? Obviously, with NASA's fiscal year 13 budget, there was massive cuts to robotic science missions. What were your thoughts on that, and what do you see as the next big campaign? Thank you.
That's a good question. I think the answer, unfortunately, is we don't know necessarily inside the Mars program, which is where I do most of my work. There's new budgets for the entire planetary team to be thinking about as a result of this last budgetary cycle. But the Mars program in particular is looking at our allocation going forward and trying to decide what to do. Historically, we had intended to embark on something called a Mars sample return campaign, where the idea was to collect a sample, launch it off the surface of Mars, put it into orbit, and then we'd have an orbiter that essentially do rendezvous with that sample and bring it back to Earth. There's a lot of interest in the science community, I think, in still doing that. We go through, once every 10 years, we go through this thing called a decadal survey where the science community comes together and decides what the prioritized missions are. And Mars sample return, actually bringing a sample back to the Earth, was at the top of the decadal survey exercise. But it's recognized that that's an ambitious goal, and we have to assess the budgets and determine whether or not that's a campaign that makes sense within the current budgetary constraints. It may be that we can stretch it out in a way that would make sense. It may be that we ought to be looking at some of the other priorities that came out of the decadal survey. We don't know, actually. But I've been spending a lot of time actually trying to help the program answer that question over the last 3 to 4 months. And there's a lot of exciting options out there. It's just a question of figuring out which one sort of fits our current environment.
I was able to catch you when you came in, and we've already talked. When it comes to the 6th of August, can you do anything about holding the machine, stalling it and holding it for a day or two, or not? Why the 6th of August?
Yeah, there is the Viking lander, which landed in the late 70s, went into orbit around Mars. And so they had about 3 weeks to decide, okay, it's time to go down, which is the type of capability I think you're asking about. These do not. These systems are too big, they're too heavy to put into orbit. They're ballistic trajectories right into the outer atmosphere, and we have two options. We either land on Mars or we miss Mars, and I'd rather try to land on August 6th. So it's one way or the other, we're heading for the surface of Mars, I think. Yeah. Yeah, I was. We talked before the talk, and I was explaining my sort of circuitous professional route into this strange business that I do of planetary science. And I started out actually in the Navy, and spent a bunch of years as a submariner, as we talked about. And so it has some interesting parallels, but the engineering associated with submarine systems, I think, were a good start for me, and some of the leadership skills and those sorts of things obviously were fed well into some of the work I do now. But I eventually left the Navy and ended up doing what I'm doing now, and I enjoyed both careers. So,
you mentioned briefly about redundancy on the rover, but I was concerned about what sort of redundancy you've got in the entry descent, the descent module, and in the sky crane itself.
Yeah, so almost by nature, entry, descent, and landing is a single string operation. It's if you have a hiccup, especially with the closed-loop guided control system like we have here, there's really no time to respond for the most part. There's a few graceful degradation modes that we've built into the system, but it's kind of a one-pass deal. You don't get another shot at it. All the pyrotechnic and release devices have to operate. They have to operate down to the second, in some cases down to the sub-second in timing. The computer has to find solutions, navigation solutions quickly. The radar has to identify the surface and get a good altimetry and velocimetry, measurement. So the entry, descent, and landing system, part of the biggest challenges of these systems is that they have to be extremely reliable. There's just no, okay, let's stop and think about how to fix this sort of opportunity for entry, descent, and landing. So all of our software systems, for instance, right? There's no, screen can't freeze on this. And if you can imagine, that's one of the things that drives the cost just enormously, is to try to build in that kind of reliability into the system. There's a lot riding on it. But entry, descent, and landing, because it's so mechanically oriented and because the timing is so critical, is fundamentally single string. Even if we had extra hardware on board, in case a piece of hardware failed, we probably wouldn't have time to boot it up or to transfer our control system over to a secondary controller and things like that. Now, as I said, we have some back doors that we throw in there, some of which we think would work if they need to, some of which we're not sure if they would work if they, but fundamentally we approach this as something where everything all of these systems have to work. There's really no backup. There's really not any redundancy in the
I was just wondering if we were able to monitor this on the web through NASA TV or some other function so we can watch as you're watching, assuming you get your satellite in the right place.
Yeah. Good question, and I should know the answer. I'm sure NASA TV on the web is going to be covering it, and that might be your best bet. I'm not exactly sure what the networks are doing in the United States, and I'd be even less sure what's happening here. But certainly NASA TV is going to come online about an hour and a half before landing, and they're going to start webcasting interviews and technical data and that sort of thing. So we land at 10:30 p.m. Pacific time, which is 6:30 or 5:30. I can always get this 6:30 your time. So you're going to have to get up early, but it might be worth it. The orbiter, as I said, for the first part of the mission, we actually have a direct line of sight back to the Earth. And so up until post-parachute deploy, we'll actually be able to see the signals directly from the spacecraft. Then we kind of go over the horizon, the Earth sets, and we have to relay everything up through the orbiter if we're going to do real-time feedback. So even if the orbiter does not get positioned successfully for the full entry, descent, and landing cycle, we'll have good data for a good part of the entry, descent, and landing activity. And then, barring something new, we would expect to see data very shortly after we land. As I said, it's only 7 minutes from the top of the atmosphere to the surface, and then last I checked, I think the orbiter pass is on the order of 2 minutes after we land. So it should come pretty quickly.
I'll have to bring the talk to a close now. But thank you very much for a fantastic talk and very, very open and good answers to the questions. I'm sure we'll all be up early on the 6th of August with our fingers crossed, wishing you every success on this mission. It really is truly fantastic.
Thank you.